This conference will now be recorded.
So very good evening, students. We were discussing this question yesterday. We'll recap a little bit and we'll see the other options, how we can solve and see whether all the options. So this is actually from uh, IIT JEE advanced question. In this question, it is said that in the circuit, this is from electricity and current and electricity. As you see, this is uh, the circuit given in this figure. So in the circuit above, the key is pressed at time t is equal to 0. Which of the following statements is or are true? So there will be multiple options correct maybe. So we'll have to check all the options. So yesterday we had solved for the first part. We'll just recap what we had done yesterday and then we'll see the other options as well. So look, when the key is pressed, immediately after that, see the voltmeter, the first option says the voltmeter display -5 volt as soon as the key is pressed, and it display shows +5 volt after the long time. So how to solve this? Yesterday we had seen how to solve it. See, we can use Kirchhoff's voltage law, and before that we need to know some characteristics of capacitor. You know, the character of capacitor is that, so when you have a capacitor and connected to some battery, okay, and suppose it is charging through this circuit, okay, this is some capacitor C and this has voltage B, this is resistance R, okay. So what happens, as soon as the battery is switched on, current starts flowing, okay, current starts flowing, and in the initial condition, initial stage, as soon as the key is pressed, so this will not have any charge, so therefore it doesn't develop any voltage, okay, it doesn't develop any voltage across these plates. So what will happen, because the charge is here 0 in the initial stage, like as soon as the switch or key is pressed here, so the the capacitor will act as conducting path, okay, it will act as a conducting path. All right, so capacitor will act as conducting path, okay, conducting path, and there will be no voltage drop across, like voltage develop across these capacitors. Now when, after this is actually soon after switching on, soon after switching on, this situation is soon after switching on, okay. And another case is, like, see, after long time what will happen, the same voltage will be across this, okay, so same voltage will be across this uh, capacitor, so there will be no voltage difference between this point, suppose A, and this point B. So if there is no voltage difference between these 2 points, so there will be no current flowing through this, so current flow will be eventually 0, so it will actually act as an open path. So after long time, capacitor acts as an open path. After long time of switching on the key or switching on, let us say the switching on, capacitor acts as a an open path, as an open path. Open path means there will be no flow of current. So with this concept, look what we can do. If we just take this, there are actually, suppose there are two loops. This is L1, this is L2. Okay, we can actually use Kirchhoff's voltage law, Kirchhoff's voltage law, KVL, KVL, applying KVL for L1 and L2. Okay, I'm sorry, these are not L1 and L2. I'll just tell you what is L1 and what is L2. So I can actually take two loops, L1 and L2. See, L1 here, I'll just take, let me just give some name. Let us say this is A, okay, this is B, this is C, this is D, this is A, E, okay, and here the other path is, or other way, we'll give A, B, C, D, E, here this is F, okay. So look, the L1 I have chosen, suppose A, F, C, D, E. This is L1, loop L1. We'll apply KVL for that. So if we apply KVL for this particular part, A, F, C, D, E. So what we can say here, see, first of all, there will be no charge in this. So it will act as a conducting path. So no need to worry about it, right? This capacitor, we will not worry about capacitor at all. I'll just see. So suppose there is a current I1 flowing through this way and I2 flowing through this way. Okay, that is what I'll consider, or it can be either way also. Let me just take this as, for convenience, this as I2, this is I2, this is I1. So this is loop 1. So loop 1, no, this is I1, this is I2 I'm taking, I'm sorry. So I1, I1 through this branch A, B, C this way, and I2 through this A, F, C, D in this path. Okay, so L1 is this loop. So in this actually we see, if I say I2, I2 into 50 I2, 50 into I2, 50 into I2 is equal to this 5 volt. Okay, so what is 50? 50 actually 50 kilovolt, kilo ohm. Here actually this is kilo ohm. Okay, there is some mistake in this figure. So kilo ohm, and when it is kilo ohm, I have to write 10 to the power 3 over here. So I2 can be found out if required. So 5 by 50 into 10 to the power 3. So it will be 0.1. Okay, 0.1 milliampere. Okay, 0.1 milliampere. Okay, so what is I1? See here in this way, if I apply KVL to this loop 2, loop 2 is A, B, C, D, E. Okay, this way, and A starts like this. Okay, so here A, B, C, D. See, A, B, C, D, the whole outer one. Okay, so here if we apply KVL, what we get? KVL, see, this is also here I1, right? So 25 into 10 to the power 3, I1 is equal to 5 volt only. Okay, 5 volt. So from here, if we see, we'll get I1 is equal to 0.2 milliampere. Okay, so we have got the currents. Okay, so what we have got? We have got currents through. So this I have taken I1, and through this I have taken I2. So I have got I1 is equal to 0.2 milliampere, and I2 we have got 0.1 milliampere, right? Now I have to find out the voltage. Okay, voltage I have to find out. See, I can now do one thing. See, in this branch, this this branch, the current is flowing is actually okay. So now what we can do is we can again, let us say this is B, this is A. I can just take another loop L3 here. Okay, this is L3 suppose. Now if I write KVL for this L3, what we will get? KVL for L3 through this resistor, through the resistor of which current is flowing. This is I1 flowing here. Okay, just see that I1 flowing through this way. Okay, and this is, see, this part is connected to positive terminal, sorry, negative terminal of the battery. So this plate of the capacitor will be negative and this plate will be positive. Okay, now if I apply KVL for this particular loop, like a a B and C, this is suppose C, this loop L3, A, B and C, this L3 here, if we apply KVL, what would we get? We'll get, see, let us suppose this point has some potential VA, okay, VA. So, and this point has potential VV. So what we can get is from here that VB, see, here it is positive, here it is negative potential. This is negative because it is connected to negative terminal of the battery. So here also in the voltmeter also it is shows negative. So this is negative, this is positive. So you can write VB minus VA. This is equal to the current through this. Okay, current through this. So this is the situation when I am just considering that there is no charge across the capacitor. Okay, or no voltage across the capacitor. So that is what I'm just taking, like as soon as the key is pressed. So that's why I'll take 25,000 into I1, simply this one. Okay, so B minus BA, this itself will show you the voltage of this particular voltmeter. Okay, so again, one more thing is that, see, the VB is positive, B is negative anyway, but the here actually, see, if I take this as positive voltage, this is negative. Again, the current, I'm going from this way. Okay, loop is like this, and current is flowing in the negative direction. So that's why here there will be a negative sign. Okay, in the Kirchhoff's law. So this is how, if we see VB minus VA, again, see, this is 25 into 10 to the power 3, and I1 is 0.2, 0.2 into 10 to the power 10 to the power minus 3. So this 10 to the power 3, 10 to the power minus 3 goes off, and here it will be 50, so minus 5 volt. Okay, so the voltmeter shows minus 5 volt as soon as the key is pressed. Okay, so this part is fine. So we have got this part is correct. Okay, when the voltmeter is, as soon as the voltmeter is on, the voltage shown by this voltmeter will be minus 5 volt. See, I can actually directly say this also. Why? Let me just erase this portion. I can, without doing any mathematical calculations, I can say that will show minus 5 volt, because you look, if these are conducting wires, this is conducting wire, this is conducting wire, so the whole voltage will be actually dropped across this resistance alone. So you look here, this point, if it is conducting wire, that means this voltmeter is connected here somewhere. Okay, here, let us say, and this resistor is there connected to this. So I can just say that 50 volt, see 50 ohm, kilo ohm, sorry, this is kilo ohm, and so this circuit actually can be replaced by, see, this is, if I just pull it, I have these two resistors. See, this is 5 volt battery, then ammeter, 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 then I have this conducting wire, this is resistance, this will come to directly to this part. Okay, so voltmeter is actually connected to, okay, so here this is 5, anyway this point is gone, this point up to here we have come. Now this part, along with that, this voltmeter is there. Okay, so voltmeter is connected 25 ends. Okay, so this is here at the end of this. Okay, in fact you can see voltmeter is here. Okay, these are actually connected to parallel, kind of that you can think. Okay, the whole voltage is actually, whole voltage is across these two resistors, that means 5 volt. Okay, but the polarity you have to check, this will be negative only, negative polarity. So why I'm saying this, because see, if there is no voltage drop across these capacitors, look here, the minus 5 voltage is here. Okay, and here it is connected to this way, this, so plus 5 volt is here. Okay, so eventually it will be shown minus 5 volt. Okay, all right, so sorry, this is minus and this is plus. Okay, all right, anyway you can just go this way just by applying Kirchhoff's law. Another part, similarly we can just see, after long time, we'll see that after long time what happens. After long time, after long time, long time t, so long time, let us say that is t. So what will happen, I1 and I2 both will be actually zero, both the currents will be zero after long time. So if the currents are zero, then what we can write, we can again write the Kirchhoff's law. Kirchhoff's law, so how we can write Kirchhoff's law, we can write for one capacitor, so suppose for this 40 microfarad capacitor, so for this we can write 5 in fact whatever loop we had shown you in the beginning, A, B, C, D, E, then this is F, suppose. So the loop A, B, C, D, E, A. For this loop, what we can write? Kirchhoff's law. We can write that. So this we can write 5 volt, and this is minus of the voltage across this. Okay, so that is Q1. Suppose it is holding charge now Q1, and this stores charge Q2. So Q1 by C1, that is 40 microfarad, and this also will be microcoulomb only. So this micros we can just remove now. Okay, so this is equal to zero current is zero, so drop across this 25 kilo ohm resistor is zero, so we can make it zero. So from here we actually will be able to get the charge to be 200 microcoulomb. Okay, 200 microcoulomb. Similarly, if we apply Kirchhoff's law for A, C, D, E, A for this particular loop, what we can write? Similarly, in this case also we can write 5 minus Q2 by 20, so which will give you that Q2, the charge, to be 100 microcoulomb. So once you get these charges, then can you find out the voltage? Can you find out the voltage? See, now what I'll do, see, I'll just choose a loop. I'll choose this loop. Suppose this loop I'll choose. Okay, loop BFC. Okay, BFC. So here look, this is positive, so I can find out the voltage if this voltage difference. So here suppose VF is the voltage for this particular point, and this particular point VB. So VF minus VB, this will be is equal to the voltage which is stored, like voltage across this capacitor alone. Okay, so what is that? That is Q2 by 20 microfarad, and Q2 we have found out 100, right? So this is 100 and divided by 25, 100 microcoulomb, and this is 20 microfarad. So this would actually give you 5 volt. Okay, so that's how we can see that after long time, as the currents are zero, the voltage across this, like voltage shown by the voltmeter, will be 5 volt only. Okay, so this is how we can solve this problem. First part. Second part, we'll see how to solve it. So second part, we'll just write down. See, we know when capacitors are charged. See, the second part is saying voltmeter will display 0 volt at time t is equal to 0. So any arbitrary time. So let us see what is the equation of charging at any arbitrary time. What is the charge stored by a capacitor? In general, equation will be charge Q is equal to Q0 into 1 minus e to the power t by CR. What is C and what is this Q0? Q0 is C into V, and this is 1 minus e to the power t anytime t, okay, by CR. So this is actually charge stored on the capacitor at any time, stored on capacitor at t, at any time t. This is the general equation. What is this CR? Look, we can actually find out what is CR. For this particular branch, what is CR? I'm just taking this is one branch and another branch this way. Okay, so charging let us say this is capacitor C1 and this is capacitor C2. So charge stored on the capacitor 1 at any time t, C1 at any time t will be written as C1. V is 5 anyway. C1 V, let me write first V. And what is CR in this branch? What is CR? 25 into 10 to the power 3, and this is 40 into 10 to the power minus 6. This is actually time constant CR. So this will be actually 1 if you see. Okay, so here 1 minus e to the power t by CR is 1. And what is C1? C1 is 40 microfarad, and volt is 5 volt. Okay, whole into 1 minus e to the power minus t. So I can write Q1 as 200 whole into 1 minus e to the power minus t microcoulomb. This is one. Similarly, for this branch, suppose this is the capacitor C2. So for this branch, charge on the capacitor C2 after any time t, here also C into R will be 1 only. So it will be Cv is 100. So 100 into e to the power, sorry, 1 minus e to the power t microcoulomb. So we have got these two charges. Okay, so I was just recapitulating. So that's what I had written. That's why I have written this equation. So I'll just erase this equation, this part, and directly I'll write the charge on the capacitors Q1 to be 200 it is whole into 1 minus e to the power minus t microcoulomb, and Q2 can be written as 100 whole into 1 minus e to the power t microcoulomb. Okay, this I'll erase that. Okay, so we have got the charges. So can we get current at any time in the both branches? Yes, we can. We can just take time derivative of the charges, and then we can get the current in each branch. So the question is, it will slow. So this voltmeter will show 0 volt. So that is what is the question. Now look, I have to now at any time I can write, as I was writing the Kirchhoff's law for the same loop. So we can write the Kirchhoff's law. See, for this loop, like outer loop and this loop, as we were doing since beginning. Okay, we can write Kirchhoff's law, and see, I can just give a name here B, and this is A, and this is suppose C, ABC. So if I write Kirchhoff's law for this particular ABC, this particular loop, okay, what we can write? We can write, say, VB minus VA is equal to VB minus VA is equal to charge on this by so this is Q2 by 20 microfarad. Okay, Q2 by this, and see in this there is current I1 I have already chosen. So this current is flowing through this way. I'm going from this point. Okay, I'm going from this point. So what I can write? I can write here 25 into 10 to the power 3 into I1. This is what I can write. So see, when the voltage is zero, see, that means this side is 0. Okay, this side is 0, I can put. If I put 0, then let us see in the equation Q2 there is time t. So there, see here Q2 is 100 by 20. This is microcoulomb, microfarad, that will actually take care, that will be taken care. And this is 1 minus e to the power minus t. And here it is, see, I have to find out I1 and I2. So what is I1? Let us write it here. I1. I1 will be how much? We'll just take derivative, time derivative. So time derivative of this, so dq1 by dt. So this is, see from here, this will be there. So e to the power minus t with a minus sign, so the multiplied with that. So this will be like this only. This was actually microcoulomb. So we can put it here directly as microcoulomb. Let us see what we can write here. 25 into 10 to the power 3, along with that this, so 200 into 10 to the power minus 6 into 10 to the power minus t. So if we just see, this is 5 into 1 minus of this, okay, and here we can write, this is, see, this is 25, so you know this will be 25 into 2, and this 2 and this 3, so there will be minus 10 here, so this is minus like this, okay. So this will be 1 e to the power minus t. This is actually 5, so 5 here. All right, so this will be 5 again here, e to the power minus t. Okay, so you look here, yes, this is correct only. So we have to find out when the voltage is 0. Voltage is 0. Okay, look here, we have already put this 0, so we'll take this side. Okay, this is 0. Okay, so if we take this side 10 to the power this, sorry, yeah, 5 e to the power this 5, and this is minus of 5 e to the power t. Look this way, we'll bring here 5 is equal to 5, so 2 into 5 e to the power minus t. This is what it is. Now this is, so 2 is equal to e to the power t. Okay, 2 is equal to e to the power t. So t is equal to ln 2. So this is the option ln 2 second. So look, I have done the calculation. It is looking little bit messy, but you can just make it out. What I have done, I'll just erase this part, rather I'll go right hand side. This is a very lengthy question and also little bit conceptual, so that's why it is taking little time. So see, from this point what we can write, this side is 0 anyway, we have already put it 0, and we are finding out the time. What is the time? So you look here, we'll get 5, and this is 10 e to the power minus t is equal to 0, right? So then we get 5, this is 10 e to the power minus 2, so e to the power t is equal to 2. Okay, because this I can write 1 by 1 over 2, 1 over e to the power t. So from here t is equal to ln 2 second. Okay, so ln 2 seconds is the time when this will show voltage 0. Okay, voltage 0. Voltmeter will display 0 voltage at t is equal to ln 2 seconds. So this is also a correct option. Okay, no doubt this is also a correct option. We'll go to the next option. The current in the ammeter becomes 1 over e of the initial value after 1 second. So we have to see what is the initial value of the current. What is the current in the ammeter? Current in the ammeter will be, actually, see, current in the ammeter will be I is equal to I1 plus I2. Okay, so we have got expression for I1 and I2, as you remember. See, I1 we have got, see, what was Q1? Q1 was 200 e to the power minus 1 to the power minus t, and Q2 was, so I1, I'll write directly I1. So I1 was, see, this is 200. So here one minus will be multiplied, so it will be e to the power minus t, and it will be actually micro coulomb. Sorry, microampere. Microampere. This is current, so it is microampere. All right. And see, similarly, this is 100 into 1 over, sorry, 1 minus e to the power minus t. This is microcoulomb. This is microcoulomb. This is also microcoulomb. And so I2 will be 100 into e to the power t microampere. Right? So these are the expression for the current. We can just add them to get the total current for the ammeter. So total current in the ammeter will be 200 e to the power minus t plus 100 e to the power minus t. This is microampere. So it will be 300 e to the power minus t, right? Microampere. So if you just want to make it to ampere, so what you need to do is 300 into 10 to the power minus 6, right? We can just make it milliampere maybe. Okay, or let it be like this. Okay, for the time being. So now at t is equal to 0, that is the initial current. Initial current at t is equal to 0 will be 300 microampere, right? 300 microampere. At t is equal to 0, it will be 300 microampere. Okay, let us see. When t is equal to 1, so when t is equal to 1, what is the current? What is the current when t is equal to 1? T is equal to 1 second, then it will be 300 e to the power minus 1 microampere, and that is equal to 300 by E. See, the question is the current in the ammeter will become 1 over E of the initial value. So initial value is this much, 300 according to our calculation, and after 1 second, see, at t is equal to 1 second, I just put t is equal to 1 here, so I get 300. So it is actually 1 of the of 300 microampere. So this is the initial value, right? I0 is the initial value. So this is I0 by E. So this option is also correct. Last option, the current in the ammeter becomes 0 after a long time. This is true. This is true because the voltage developed across these capacitors will be same as the voltage of the battery. Okay, so that's how current will be. After a long time, current will be 0, as we know, in the capacitor. So this option also correct. So look, this question, this is very, very interesting question. This circuit looks very simple, uh, but the dangerous thing is that all the options are correct. Okay, all the options are correct for this question. Okay, So we solved this question, very interesting question. Now we'll go to the next problem. We have got a problem here related to galvanometer. Let us see. Let us try to solve it. So this is also from JEE Advanced 2014. So the question says a galvanometer gives full scale deflection with 0.006 ampere current by connecting it to a 4990 ohm resistance. Let me just explain you the first line itself. So suppose there is a galvanometer. I'm just drawing the schematic. So this is galvanometer and the associated resistance is Rg. Okay, so this is the galvanometer. Okay, so galvanometer shows full scale deflection with this much current. That means the current through the galvanometer Ig will be this ampere. Okay, that means it is 6 milliampere. Okay, 6 milliampere. All right. So the current through the galvanometer, full scale deflection of the galvanometer is shown at the current which is allowed through the galvanometer, that is actually Ig. So whenever there is full scale deflection with some current, that particular current will be Ig through the galvanometer. That you have to take. Now by connecting it to a 4990 resistance, it can be converted into a voltmeter of range 0 to 30. So when there will be range, we will take the maximum limit of the range. Okay, maximum limit of the range or maximum range will take will for the calculation purpose. So see voltmeter, how voltmeter is constructed from the galvanometer. For constructing a galvanometer we have to for constructing or converting a galvanometer into a voltmeter, we have to connect a very high resistance, suppose this is R, with the galvanometer in series. So we have to connect a very high resistance with the galvanometer in series. So now you look, now what happens? The whole voltage range means, see if you just take a voltmeter, so this is actually now will show the range of the voltage range 0 to 30 volt. So actually across this, as I said, I'll take the total voltage, the maximum range. So total voltage drop across this and this will be 30 volt. That is what we have to take. So total voltage drop across this will be 30. So how we can write that? So Ig into, so same current is flowing through both the resistor. Okay, Ig into Rg plus R, this is equal to 30 volt. This is one is the first equation we can write. Okay, so this is first equation. Okay, from here what we can do, since we know this R is here given 4990, we can find out what is Rg. Let us find out what is Rg. Rg will be 30 volt by 6 milliampere 10 to the power minus 3 minus of R. Okay, so this is 30 by 6 into 10 to the power 3 here, and this is 4990. This is 5. So let us say this is 5000. So this is 5000 and this is 4990. This is in ohm anyway. This is in ohm. Okay, so we get Rg to be 10 ohm. So galvanometer has resistance 10 ohm. Okay, so this is what we have got. So next part is if connected to a, so sorry, this is actually this is 2n by, actually this is 2n by 249. Okay, this is 2n by 249 ohm. So if connected to a 2n by 249 resistance, it becomes an ammeter of range this. Now look again, this particular arrangement. Now we have, see, we have this galvanometer. This galvanometer, if it is connected, if we want to convert this galvanometer, see, I have the galvanometer, this is Rg, current flowing through this is Ig. Now if I want to convert into ammeter, what I should do? I should actually connect a very small resistance, some S in S with like parallel to this, or as a shunt. This is shunt resistance I have to add, okay, with this galvanometer. And the range of the current shown by this ammeter is 0 to 1.5 ampere. That means the main current should be this, okay, this much. So this current is suppose this is I. This current is flowing through both this, like this is the main current, this is the range of the current shown by ammeter. Okay, now so this current will be actually divided into two parts. One is Ig and another one is I minus Ig, right? So how to find out this value? We know that very well. See, we can write S into I minus Ig. This is Ig into Rg. So this is the equation. The question was, what is the value of N if 2N by 249 ohm resistance is connected to the galvanometer? It becomes an ammeter of range 0 to 1.5 ampere. What is the value of N? So that is the question. So what is the value of N? We have to find out. So we know S is 2N by 249, and this is 1.5 minus 0.006 ampere, and this is again Ig we have 0.006, and this Rg we have got 10 ohm, right? So this is what was the thing. Now we'll do one thing, we'll just find out what is, this is 5. Okay, so 5 into 0.006, and see, this will be 249 divided by 1.5 minus 0.006. Okay, this is what we have to actually solve. So 1.5 minus 0.006, so this will be 494, 1.49. Okay, so look this, let us first write 0.6006 into 259 divided by 1494. See, what I'll do, I'll just approximate this to be 1.5 and this to be 250. Let me see. So this is 5, this is 0.006 into 250, let us say, and here it is 1.5, say. Okay, this will be, so this is, sorry, we can just multiply 110 over here, so it will be 3. Okay, 3, and here 110 I can multiply, so it will be here 0, right? And see, this 2 0, so 0.6 over here. So look, if you just solve it, you multiply here, say this to 10 to the power minus 3, right? So 6 into 10 to the power minus 3 I'm writing here, 6 into 10 to the power minus 3. So this is 2, and see this goes like this, 2 to go, so 110 will be here. Okay, this will be 5, and this 5 will be 5 here. So this is 5, 5. So the value of n will be 5. Okay, the value of n is 5. So this is how we can solve this problem. Now we'll go to another problem. So this is related to an incandescent bulb. So this question says an incandescent bulb has thin filament of tungsten, that has that is heated. Okay, let me just read the question. An incandescent bulb has a thin filament of tungsten that is heated to high temperature by passing an electric current. The hot filament emits black body radiation. The filament is observed to break up at random location after a sufficiently long time of operation due to non-uniform evaporation of tungsten from the filament. If the bulb is powered at constant voltage, which of the following statements is or are true? The first statement is the temperature distribution over the filament is uniform. The temperature distribution over the filament is uniform. Let us first see with this option itself. See, the distribution of the temperature over the filament is uniform. This is not true because see, this is written sufficiently long time operation due to non-uniform evaporation of tungsten from filament. So here itself it says that temperature distribution is not uniform. Okay, so this is not a true option. Now the second option is the resistance of small section. The resistance over small sections of the filament decreases with time. So this also may not be true because the filament is made of tungsten. Tungsten doesn't have this property. Okay, only only semiconductor has this properties. Tungsten is a conductor, so conductor doesn't like temperature of a conductor. Resistance of a conductor does not decrease with time when it is heated or when current is flowing continuously, or a constant voltage is applied already. See, if the bulb is powered by constant, okay, powered at constant voltage, so there is no reason for the resistance to decrease at some places or some sections of the filament. Okay, because it is a conductor. Now let us see the third option. The filament emits light at higher band of frequencies before it breaks up. The filament emits more light at higher band of frequencies before it breaks up. So it may be true because like anything you heat up, when you heat it for a long time, see initially it will be some yellowish. Suppose you take an iron piece, it will be yellowish, then it will be a kind of red hot, and finally it will be actually white hot. So white hot is actually at very high frequency. Okay, the light has high frequency. Okay, compared to red hot and all. Okay, so when you heat this filament for a long time, so it will be kind of like white hot. Okay, so color will become white, so the which has actually light of frequencies at higher bands. Okay, and for tungsten maybe it goes maybe again for higher frequencies. Yeah, this is true. Okay, so as you heat for a long time, because uh, higher and higher frequencies of light will come up. Okay, that is true. And the last option is the filament consumes less. Filament consumes less electrical power less electrical power towards the end of the life of the bulb. Towards the end of the life of the bulb. So towards the end of the life, the filament will become thinner. So if it is thinner, then resistance will actually increase. So consumed power will be less, because we know power is V square by R, constant voltage, right? V square by R. So power consumption will be less, because the see, thinner means greater resistance. Okay, greater resistance. So filament will become thinner and thinner. Okay, at the end of the uh, life of the bulb. Okay, so this is how the resistance will be raised. Okay, so that's why this is also true. It will consume less power at the end. All right, so with this we will stop with here for today, and thank you for your patience. We'll meet again with some more JEE advanced question on this particular chapter in the next classes. So bye for today.